Our speaker this morning is Tapasi Ghosh, and she'll be talking with us about the role of large single dishes in VLBI. Take it away, Tapasi.
Thank you, everybody. So we so far haven't talked about VLBI, so I'll just go over a little bit of basic concepts, and then that basic concepts of VLBI obviously involve basic concept of interferometry itself. So we start there very quickly, and then talk about VLBI, give you the large single dish perspective and a few scientific results. And feel free to stop me at any point. Okay. I don't have my camera on. I apologize. Right now with this screen share, I'm unable to put my camera on. Also for the data rate, it's better if I stay with the camera off. I'll come back on at some point. Okay, next one. Okay, so the basic concept of interferometry itself, we can start with this Young's double slit experiment, which many of us might have done in our optic classes, where you basically have a screen, a monochromatic light source, a screen with two pinholes, and then a screen where the light from the two pinholes for interfere and form dark and bright fringes. So that dark and bright fringes basically the spacing of that depends on the separation of the two two pinholes. So that gives you an indication about the size of the objects. So using this concept, one can basically study the structure of an object in more detail. the the salient points here are the constructive interference. Basically, the bright lines are made at when this equation is satisfied. D sine theta is n lambda, where D is the separation between the two holes, and theta is the angular this angle between the observing point and the midpoint. And fringe spacing here is defined by lambda by D. Now, and then another important concept here, the contrast of the fringes, which is called fringe visibility, and it's measured by maximum intensity minus minimum intensity divided by the average intensity. This is the so-called fringe visibility. So if you have a point source here, then what happens is your fringe visibility is basically almost 100%. Okay, and you see the contrast very well. A radio equivalent of that is you have two radio telescopes, and they're looking at a radio object from this direction, say, and the signal are multiplied and integrated over, which we call correlation. Basically, they're forming, when you multiply and integrate, you're basically forming the cosine fringes of this fringe pattern here. Here again, this the difference in the path length between the two rays in this diagram is giving you the phase difference that's causing the fringe pattern at the recorder, and that is basically determines the spacing of the fringes. Okay, and ultimately that determines how finely you can resolve things in the sky, on the sky. Okay, this is the basic idea at the heart of interferometry. Now, if a source, when you track a source across the sky, what happens is this is telescope 1 and the telescope 2, as seen from a direction in the sky. Basically, this vector, or the what we call the baseline vector, basically traverses an ellipse. on a plane that's perpendicular to the direction of the source. So imagine a plane on the surface of the earth that's tangent to the direction to the sky, and there the baseline vector traverses an ellipse. Okay, so as the source, if we didn't do anything, just track a source and the earth rotates, the baseline vector makes this ellipse, and the two components of that along north, south, and east, west are called U and V. And these UV tracks is basically makes your UV coverage. You must have heard the term UV coverage, and if you're familiar with interferometry and have done interferometric map analysis of maps and made maps yourself, you probably have dealt with UV coverage and UV coordinates and visibility as a function of U and V. So we'll come to that. So it basically, it tells you what, basically, this is your synthesized telescope, and that determines the resolution of the map that you're making, spatial resolution of the maps that you're making. Oh, sorry. Now what happens if we have an extended source? So far we're talking about a point source. If we have an extended source in the coordinate kind of a coordinate system, and the sources plane on the plane of the sky, say this source is extended, its central point, which we call the reference point or the phase center of the point of the source. Relative to that, it has a size. So let's define a vector omega here, sigma here. And so each point on the source will basically make a set of fringes on the sky, on the recorder plane where we are recording the data. And what we are recording will be vector sum of all those fringes, right? And how much phase we have to shift each of the fringe pattern by depends upon the separation of the point in consideration relative to the phase center. So that phase factor comes here, and basically this will be a recorded visibility coming from all the point sources that make up a particular source. So this is called the visibility function. And now if we take a look at this equation very carefully, what's happening is what we are measuring, the visibility function, is nothing but the Fourier transform of how the intensity is distributed in the plane of the source. So alternatively, we can say that our aim is to basically determine this. This is what we're interested in, but we're measuring this. So how we're going to get from this to that? We do an inverse Fourier transform. We measure as many components of this visibility function as possible. And then we do a inverse Fourier transform, and we get from visibility measurements to the intensity distribution of the source, which is from measured visibility as a function of U and V, which makes the baseline vector as I defined earlier, and then you get to intensity distribution of the source. Okay, so you can read up a lot about this. There's an awful lot of literature research that has gone into making all these things possible, but I'm just, not even at the top level of the surface, just very, very basic ideas that I'm presenting here. So now let's look at some of the examples, how that happens. So here, I'm talking about a few Fourier transform pair. So if your image is just a point source, your visibility is going to be same everywhere. And sometimes this is a two-dimensional plot as a function of U and V. Sometimes people like to look at it as a one-dimensional plot. Basically, you take U square plus V square square root, basically the amplitude of the baseline vector, and plot your visibility, measured visibility as a function of that. And it stays unchanged. So the Fourier transform of a straight line that doesn't change is the point source, is a delta function. So these two check out. If you have an extended source, then your measured visibility becomes this beautiful concentric rings with diminished intensity as you go out. And in one-dimensional plot, in a radial plot, it looks like this. So it's like almost like it's a sinc square function, so to say. So anyway, so if you do a Fourier transform of that, if you measured all these values and you can define this curve beautifully, you do a Fourier transform on your computer and you get a perfect source. However, nothing is ever perfect. So what happens is, what we get is this dirty image. The reason for that is we don't have all the visibility values measured up to a certain range. So because of limited time, limited resources, limited number of antennas, and all of that, our UV coverage, meaning measurement of visibility at all UV points, is not complete. We have incomplete visibility coverage. So when you do just the Fourier transform, what we get is the so-called dirty image. Now from that, what normally people have again researched all of this an awful lot. So you use various deconvolution methods. What is happening here is that there's this perfect image on the sky, and that got convolved because of our imperfect beam, incomplete UV coverage. It got convolved with a beam that is, say, looking like this. So we have little bits of responses everywhere, and that's causing all of this stuff. So we deconvolve this beam from dirty image, then we can get a beautiful deconvolved clean images. So there are various methods of doing this. There are many softwares for doing this. So that's how then at the end you could get all those beautiful radio maps that we usually see. Examples of arrays, the VLA, which is now, it's called EVLA, which is extended VLA. It has 27 antennas. Each antenna is 25 meter in the form of a Y. They are on rails, so you can change the configuration, and they're scalable. This is a beautiful instrument. And many of you might have used it. And it's been, I think it was inaugurated in early 1980s. So of course it has gone through modification, and extended VLA came up, I guess, about 10 years ago. I'm not exactly sure. It's a beautiful instrument. Lots of research coming through this. Then this is a synthesis telescope in India. It works only at lower frequency, only up to L band. It's also very nice instrument, open to everybody. Then this is a millimeter interferometer in Chile. It's in the high dry plateau of Atacama Plateau, Atacama Large Millimeter Array. It's again a very beautiful instrument. So these are just examples. Other telescopes coming up. The common thing about all of them is the signal from all the dishes in these all three cases are brought together to a central processing place. They are all connected element interferometer. So as you are observing, you're basically getting your data instantly. You're forming those visibilities right there as you're observing. So what is VLBI? It is radio interferometry, but with physically unconnected antennas. So there's no cable really connecting them. And when that happens, what you can do now is you can place your antennas quite far apart, as long as you are looking at the same sky, same part of the sky at the same time. You can use two antennas. So the physical restriction of having to connect the signal at the time of observing goes away in this case. That gives you very regularly very high angular resolution, milliarc second resolution or better. It's very standard thing to get. Baselines up to the Earth's diameter. Also, there have been for the ground-based VLBI, and it has been extended to space. There had been a Japanese station called VSOP or Halka that was operating in the early 90s. And then there was a Russian radio astronaut satellite, which just finished a couple of years ago. So these gave you huge spatial resolution. Traditionally, it uses no IFLO link, as I said before, between the antennas. Atomic clock for time and frequencies use hydrogen maser. In case of radio astron, there was really one interesting thing that happened from Green Bank, that the hydrogen maser signal was actually sent up to the link at some point. Earlier, there was an onboard hydrogen maser that failed. And then at that point, hydrogen maser signal was signaled up to the satellite, and that worked too. So that was a nice thing. The data are recorded on disk-based temporary storage, and then they are transported to a common correlator. And there, the data correlation happens after the fact. Sometimes there's also using data sent real time over the internet, and these are called eVLBI. In Europe, this is happening more regularly. From this side of the waters, Arecibo participated in eVLBI quite a bit, and not very regularly, but yes, there had been at regular interval, there had been eVLBI. So these other advantage of this is one can use regular already made single dish antennas. It doesn't have to be purpose built. That has its plus points and minus points, but mostly, you can repurpose an already existing radio telescope. Otherwise, there's no fundamental difference between linked interferometer and VLBI array. Okay, let's carry on. So in the US, the standard instrument for that now is the VLBA. It has 10 25-meter identical antennas distributed across the US from St. Croix to Hawaii. And Green Bank and Arecibo participated. Arecibo's no more, but it did participate as much as possible. And Green Bank is still carrying on doing it. And at high frequency, it actually does very, very, very good job. Range of baselines go from 236 kilometers to 8,600 kilometers. Frequency range goes from 0.3 to 86 gigahertz. Resolution, 0.1 milliarc second. So it's so much at the highest frequency. Operation center is in Socorro. So you have to send the data after recording, just the voltages, not correlated yet, sent to Socorro. Other VLBI arrays around the world. This is the VLBA, as I talked about. In Europe, there's a European VLBI array, which now has 2 Chinese telescopes, maybe 3. There's another one here, participations. There's in the Korean Peninsula, there's a KVN. In Australia, there's a long baseline array. And there is some CMVA. This is a millimeter VLBI that gets arranged once in a while with all the millimeter telescopes around the world. Then these are astronomy VLBI. There's also geodetic use of VLBI. I'm not going into that at all. There's a standard global geodetic array, and which is actually operation center is in Haystack, Massachusetts. So that's a very active group as well. These are the two space antennas that I mentioned earlier. This one is Radio Astron, and Radio Astron went quite close to the moon. It was in a very elliptical orbit, so it gave a very the longest baseline so far. And this is the Japanese field, Japanese Halka telescope. Next. So a few relevant parameters. These are the things that you have to remember. There is angular resolution you get with the VLBI is, as I said, it's not the diameter of the dish that determines the velocity, determines the resolution, it's the separation of the antennas. So the farther the antennas are, the better angular resolution you get. So that's the formula for it. Sensitivity, here you have to work with the two antennas, VLBI image sensitivity, okay? And so if you have more antennas, then of course your sensitivity goes up. This is the image sensitivity. Baseline sensitivity, it depends on the two antennas. And you might wonder, how come a tiny little antenna put in space was so useful? That's because on the other side of the tiny little antennas were big antennas like the GBT or the RSU. So overall sensitivity is actually the geometric mean of the two system equivalent flux densities. So these two numbers for GBT and RSU had been very big. So they were vital to having the small space antennas for providing baseline sensitivity. Other thing we need to consider is the field of view. Field of view is determined by the beam of the biggest antenna. So for small antennas, you may have you will have big field of view, and then people now use a large field of view and then put many small mapping areas in there to basically map the entire field of view. You get a sensitivity, you enhance your sensitivity, but you limit your overall field of view by using a big antenna. So it depends upon what is your science, what you're planning to do. So you have to think about these two. And while deciding that, what guides you, what can you use? There's this EVN calculator that anybody planning to propose for a VLBI observation normally uses that. This is a very efficient one, and I think all antennas are here. So you fill in what telescopes you want, how many bandwidth, what frequencies, how long integration time. You put all of those in and say go, and it gives you answers. You know what image sensitivity, baseline sensitivity, what beam width, what all the parameters that you know that you need to match your science. So this is very essential. If you're thinking of VLBI proposal, use this. Actually, for NRO proposals for VLBI, it's advisable to include a calculation out of this EVN calculator. So is for EVN also, I think. It helps to have that calculator, that's image included in your proposal. So why add a big dish? This slide is actually showing my RSU bias a bit, but RSU is no more. So this sadly this slide is right now just serves a demonstration purpose. So I haven't updated this yet, but this was just showing the effect of a big dish for a VLBI array. So we still have this high sensitivity array where the noise level of your map uses dramatically by adding one sensitive antenna. So one can run this calculation again by, say, add all 27 antennas phased together of the VLA, or add it or drop it out, or add GBT or drop it out, and so compare what sensitivity level you're getting. Okay, this is for continuum observation. This is for spectral line observation. Now, what are the science cases when we might need this raw sensitivity? Two things are when you have a temporary, a short temporal event, like say FRB, you cannot integrate it for a very long time. Although, FRBs, you don't know when they will happen. But if you do catch an FRB, the raw sensitivity is very, very important. Although FRBs seem to be very strong. So there's that too. So anyway, this is it's a transient short duration events. There you need raw sensitivity or a spectral line object where you cannot increase your bandwidth to gather sensitivity, to improve sensitivity. There also you need raw sensitivity. So these are two clean science cases where a big dish, adding a big dish to your standard array would help you. I talked about field of view very quickly, running out of time a bit. Basically, this is becoming quite popular. People try to put smaller field inside a big field of view, but so you need to be mindful of what's happening. If your science demands that, then before just adding a big antenna, think about its field of view. Some other special consideration for large single dishes: slew times can be longer, although GBT moves very fast. Normally there is not much concern except for very cold days when the temperature goes very cold, like it is now, or last week was very cold here. So if the temperature goes below 17 Fahrenheit, then GBT slew speed goes down to half its normal speed for safety reasons. So in that case, you're slewing between a calibrator source and your other source, your target source, might not happen as fast as you expect. So the scheduling program for VLBI has all of those factored into it. For GBT, if you are scheduled during the cold months, you use a different name. You say GBT cold instead of just GBT VLBA. So that will incorporate the slew rate and give you the right estimated scan time, etc. So those things have to be kept in mind. Okay, so higher sensitivity, this is one important point. If your baseline sensitivity is high, then for self-calibration, you can go to fainter target or phase differencing observation. I haven't talked much about that, but if you're serious about putting in a VLBI proposal and you need any help, ask any of us. We will help you through. So if you are going for a sensitive antenna, then you can go to a weaker source as your calibrator. Some of the VLBI equipment, I don't know how much time do I have.
You can keep going, Tapasi. We're up against a break, and I'll probably extend the break a little bit.
Okay, I think I'll probably skip, except for saying that there had been two different worlds of equipment. So sometimes they merge together, sometimes they diverge again. So for the observatory, it has been, it can be a bit of a struggle to keep up with the changes of equipment. But so far, so good. I think we're doing fine. Most of the places right now have these so-called RDBs and Mark 6 recorder or some form of Mark 6 recorder. That's what people at the moment have. Creating a schedule. This is your important part as an user. So if your proposal is successful, you got the time, what you have to do, that you have to make this so-called example key file and then pass it through a VLBA SCADE program that's from NRO, and everybody uses that. And then the SCADE program validates everything. It creates telescope-based schedule, and they organize the sending of the schedule to various people. At Green Bank, we then run our local schedule, local kind of translator, you can call it, which creates asteroid understandable blocks, and all the observation happens without you having to be present, because this is this VLBI is always run as a service observation. We record the data and then we send it to Socorro for VLBA observation. If we join with EVN, which is called the global array, then we do the same thing and then send the data off to Europe, to Holland, in a place called Jive. The data gets correlated there, and then you get notified, you get the bits file of the visibility, basically. And from there on, you take your data into CASA or into old apes, and you make your maps. And in each of these steps, there are lots of people that will help you. There's some science. Again, I'm just going to zoom through. There was one very important result that resolved the distance controversy to Pleiades cluster. Measuring distance in astronomy is actually a big problem. So there was a controversy with Pleiades distance. Many of the ground-based measurements put the value to about 138, but then Hipparchus found a very odd value. VLBI nailed it down here. And then now Gaia also has confirmed that the value is really here, not with the Hipparchus. So this was a good achievement for VLBI in general. This is a second rung in the ladder of the distance measurements in astronomy. Okay, next one. Repeating FRB, this was just at the flash during that 1 microsecond or so. The object was millisecond. Yeah, this is the persistent radio emission, I think, of that FRB. So it helped in identification, but also there has been detection right at the time when that the flash of the FRB goes on. VLBI has nailed it down. This is some other stuff that you can do. You can make beautiful map of this basically H1 obscuring disk, where you can see the radio jets. One jet is actually coming out of the disk, another one is below. Then there are lots of other important observation. I have not done justice to any of the wonderful achievements of VLBI. One big one is, of course, all the water maser work that Jim Bratz and his students and collaborators do at Greenbank using the VLBI, where you actually measure the mass of the central black hole. So future, okay, single dishes contribute hugely. So if your science demands on those two areas, feel free to talk to us. Include GBT in your VLBI, and there's just sort of two future things I'll just mention and stop at that point. You might have seen this Event Horizon Telescope. This is at the highest possible frequencies that was, telescopes were from Antarctica to, this was the array that basically detected the shadow of the black hole here. And we probably know about NGVLA and SKA. NGVLA will have replaced the VLBA when it is done, and it will have amazingly wonderful capabilities. So there's a book with all the NGVLA's capability. It'll have long baseline options, of course, and SKA, which is being built in South Africa, that will also have a VLBI option where SKA's total signal will be correlated with the other telescopes around the world where there's common visibility. Okay, I'll stop at that point. If anybody has one very quick question, I think we can address one question, one or two.
Thank you very much, Tapasi. I don't see any in the chat right now, but if someone does have a question, feel free to unmute yourself.
Okay.
All right, hearing none, thank you again.
You're very welcome.